This is section 6.2, derivatives of the exponential function. In order to get the derivative of the exponential function a to the x, we will use the definition, the limit definition of the derivative. F prime is defined as a limit, or as h goes to 0, of f of x plus h minus f of x over h. Let's evaluate this difference, this limit for our function a to the x. We have limit as h goes to 0, a to the power of x plus h, that's what the first evaluation is telling me to do, and then minus function f of x, which is just a to the x over h. Now we have to evaluate this limit in order to get the derivative, because this limit represents the derivative of the exponential function a to the x. In order to evaluate, we have to simplify, rewrite this expression. So the first thing that we see the addition in the exponent. Since we see the addition, we may split for the product of two items, a to the x times a to the h. Since we're multiplying the same base, we will add, but we will keep this way. Now we see a to the x as a common factor. Let's factor out. I did factor out. And since the expression a to the x is not involved with h, we can consider as a constant with respect to this limit. Constant we can pull out and put outside. Okay? That's what we have. We do have a to the x times the limit. And limit, if we look closer, looks familiar to the limit actually above. After, of course, doing all of these steps, we have a limit as h goes to 0, a to the power of h, and I can consider x to be 0 with like matching to that limit 0 plus h to the power of 0 plus h, and 1 I can consider as a to the power of 0. This means that this limit, which I can use different color, the green limit, represents also the derivative of the function a to the x at 0. That means this is quite interesting fact, because it's telling me the derivative of the exponential function is proportional to itself. First of all, we see a to the x, that's the reason, and actually derivative at 0 is included in the formula of the derivative overall. Okay, as you can see, I did type at 0, and we just realized that this is f prime, this is derivative. That means it's quite interesting. In the formula of the derivative at 0 is involved. Okay? But we still have to find out this number. Okay, I can put this, and I can possibly box a little bit better. Okay, that means this is derivative at 0. Okay. Okay, that means the equation again states that the rate of change of any exponential function is proportional to the function itself, and the slope is proportional to the height, which of course we can say slope is the derivative. Okay, that's the slope. We remember slope of the tangent line, and height in this expression means the value of the function. Always the value of the function is telling me how high I will go at the certain x. Okay, but let's figure out what this limit, what this quantity is. Okay, that's we definitely know that this limit a to the power of h minus 1 over h as h goes to 0 is the derivative of the exponential function at 0. So what we will do, we will try to evaluate. I will pick a certain numbers for a, and we will investigate like numerically. So what I have a table, And approximating the numbers of the value of the limit as h goes to 0, we can see h is getting smaller and smaller, 0.1, 0.01, 0.001, and so on. And I pick, for the first one, I pick the value 2, the base 2, 2 to the x, and this one is 3 to the x. Okay. And we can see that that's the values of the limit. That means that's my f prime at 0 quantity. And if we will use the calculator and if we will keep going, this quantity actually is the natural log of 2. This quantity, you may guess, is the natural log of 3. Yeah, that we have natural log, natural logarithmic function at that base. Okay, and this quantity is less than 1, this quantity is greater than 1. That's what I can say at the moment. And let's put this together. If the base is 2, this limit is simply natural log of 2. And if the base is 3, the limit is simply natural log of 3. In general, what this means, if the base is a, this limit is the ln at a, the natural log at a. And we also know that this is the value of derivative at 0. Value of the derivative at 0. Or if we can say different way, the geometric explanation is the slope of the tangent line at 0. ln of 3, ln of 2, respectively for 3 and 2. Okay, that's when we have, of course, this is like really, really gentle proof, numerical proof, but that's correct one. And now we can come back, just the same thing that we had on the first slide, or I'm missing the okay, and now we can say that this is the ln at the base a. And what we have, we did derive the formula for the derivative of the exponential function a to the x. And I have a nice table. Right? That means that's the takes away. That's what we have to remember. Derivative of the a to the x, and I can say x is all of the real numbers. That's the domain of the exponential function. Derivative of a to the x is equal to a to the x times natural log of a. Of course, we know what this means, the slope, but that's the formula. If we combine with the chain rule, a to the power of u, of course, behind u, we have another function. We will follow the same formula, a to the u times ln of a, however, times derivative of that inner function, derivative of u, which is u prime, and that's our chain. Okay, let's maybe do one example. Differentiate 2 to the power of cosine of x plus square root of x. I can definitely write this function as a 2 to the power of u, and u is the entire inner function, cosine of x root x. And now the new formula, derivative of 2 to the power of u, is a function itself, u to the u, 2 to the u, times natural log of the base, and follow the chain rule, derivative of u. Derivative at x, it will be 2 to the power of u, and u is defined as a cosine of x root x times natural log of 2, that's part of the formula, and times derivative of u, derivative of cosine of x plus root x. Let's rewrite one more time. Derivative is 2 to the power of cosine of x plus square root of x, ln of 2, it's part of the formula. And now just differentiate cosine. Derivative of cosine is negative sine of x. Derivative of the square root of x, we do remember, 1 over 2 root x. Beautiful. And let's just derive one more formula, the formula for the natural exponential function. Okay, that's me. Let's start with this table, because having a to the x as a general exponential function, I might have e to the x. Okay, we remember, but let's actually start with this. Again, the same table, we remember that was the derivative. That means I did point this, that this is of course ln of 2, and that's ln of 3, because respectively we have that base. And I think I mentioned that this quantity is less than 1, this one is greater than 1. And both of them represents the slope of the tangent line at 0, f prime at 0. But what we actually want, we would like to have a base of the exponential function between 2 and 3, that the slope, okay, this quantity, slope of the tangent line or derivative at 0, that's the same thing, will be 1. That means now we have to think, ln of what number will give me 1? I know that you know the answer. You can pause the video and you can say aloud. Okay, we are back. The number is, one more time, that limit, which of course represents the slope at 0. We know that is the natural log of that base, that question mark, and must be 1. Okay, that's me now. Natural log of what number is 1? Of course, that number is e. And this is one of the way that the quantity e was discovered or developed. Okay? And since the number is between 2 and 3, we know that is 2.71 approximately. Okay? That means we do have also, we can say that the number e is the number satisfying this limit, e to the h minus 1 over h, it will be 1. We know why. Yeah, it's the slope. Okay, that's me now. Let's see. Here I have just the geometric explanation. Okay. Geometrically, this means that of all the possible exponential function a to the x, the function e to the x is one of those that the tangent line at 0, 1 has a slope exactly 1. We know f prime at 0, e, we know that this slope will be 1. Okay, that's me. Now let's try this. Since we know that this is 1, okay, I would like to get the formula. Now we have to differentiate e to the x. We will follow the same formula like for the general exponential function, but let's see. Derivative of the natural exponential function e to the x, it will be function itself because it's the exponential function e to the x times ln of the base, ln of the e, and we know that ln, the natural log at e, is 1. That means this is even more excited because we are more like excited because derivative of e to the x is just the function itself, e to the x. Okay. And adding the chain rule, e to the u, follow the chain rule times u prime, because behind u we have another formula. Let's solve one question. Exercise. Let's differentiate y equals to e to the power of tangent of x. I mean, I can say that my function in terms of u is e to the u, and my inner function is just u tangent of x. Derivative e to the u is just e to the u, follow the chain rule times u prime. Derivative with respect to x, I will put back tangent of x, and I can maybe speed up. Derivative of tangent is secant square of x. This will be the final answer for this question. Okay, that's when we do have two formulas. Derivative for the exponential function, general exponential function, is just the same function times natural log of a. And derivative of natural exponential function e to the x is just e to the x. Thank you.